So you're driving down the highway late one night at 16 meters per second when a deer steps into the road 37 meters in front of you. Your reaction time before stepping on the brakes is 0.50 seconds, and the maximum deceleration of your car is 10 meters per second squared. And your values might be different because mastering physics generates them quasi-randomly, so they might be different. But I'm going to solve it, and you'll see where you can substitute your own values in. Part A is how much distance is between you and the deer when you come to a stop. And part B is what is the maximum speed you could have and still not hit the deer. Remember that step one is always draw a picture. So I'm going to try and draw a picture up here. And we're going to say, so we're driving down the highway. Let's give ourselves a highway. Oops. And here's your car at the start. And here is our deer, which I really don't know how to draw, so deer-like object. And the idea is that this actually breaks into two parts, because at first you continue on before you can react. Your car keeps going at the same speed. So there you go. And then the second is you come to rest. So let's say we started with that you have some initial speed, I'm going to call it VI, and you still have that speed VI, but over here you're at rest. And you start at some position, we'll say x equals 0, and then I'll have position x1, and this is position x2, and we'll say that the deer is at position x sub d for deer. And what they're looking for in part A is they're looking for this distance, x deer minus x2. We also know that there's a deceleration going that way, which I'm going to call value A. Actually call it A initial, doesn't matter. And we know that. So for our purposes, this is the initial, is that thing. And this is xd. And this is vi. And then the thing I didn't notice, I'm going to call this t equals 0. And this t equals t1. And theoretically, I can call this t2, although I don't think it's relevant in the problem, but we can certainly do that. And we can see that this thing is going to be t1, the time between when you see the deer and the time when you start applying your brakes. All right, a lot of things, complicated things going on here, but maybe the most important thing to pull out is that this is a two-part problem wherein we will use the constant motion to generate the initial position here. And then we'll use the accelerating motion to generate the final distance, the final position. So let's walk through that. Let's figure out, first of all, where are you at the time that you start applying the brakes? That seems like a reasonable question. So we know that for constant velocity motion, the position is the initial position, right? Your final position is your initial position plus the initial velocity times the change in time. So in this case, we want to end at our position x1. That's what I'm actually looking for. I started at 0 meters, and I picked up 16 meters per second for the first half second. And so the initial place is 8 meters. So down here, I now know I'm at 8 meters. And then that problem is sort of done. And we feed that into the next problem. Then we say, well, in the second case, where the acceleration is not 0, then the final position, well, we should look at this and say, what do we have? We have, before I do that even, in this final case, in the second half of the problem, we have an initial velocity and a final velocity. We have an acceleration. We want a change in position. We do not have time information. And we're not asked about time information. So that indicates that we should probably be using the v squared equation, that vf squared is vi squared plus twice times the acceleration times the change in x. And in this particular problem, we end at 0 meters per second, which we then square. We start at the same 16 meters per second, quantity squared. Our acceleration is given as minus 10 meters per second squared. And we want x2 minus x1. In fact, and we know x1 is 8. And then we, quote unquote, just do some algebra. So we're going to get that x2 minus 8 meters, isolating that by itself, is going to be 0 minus 16 meters per second quantity squared over 2 times minus 10 meters per second square. Remember, the first is 16 meters per second, all squared. The second is 10 meters per second square. So we have minus 16 quantity squared over 2 times 10. And we get that x2 minus x8 minus the 8 is 12.8 meters. So x2 is 20.8 meters. Actually, let's do this a little differently. Let's now switch to x2 is 20.8 meters, and therefore the thing I want, delta x, or right, the distance, is 37 meters minus 20.8 meters, which is 16.2 meters of distance left. Okay, part B says, how fast could you have been going with the same other information and still not hit the deer? Notice you could have been going faster because you still have some room to brake. I would argue that this point is enough of a new problem that you probably should redraw the picture. So here we are. And then we start to brake. And then here is the deer. And in this case, the car is, right here. And what do we know? Well, we know that we have some initial velocity, which is now an unknown. And we have that it is at rest at the end. We have that it starts at x equals 0, and the time is 0 seconds. But that we end up at a time, we start to brake half a second later. We don't know what this is. By the way, I have to be careful. I'm resetting all my variables, so I can't use anything from the previous problem. And then we want to say that we end up at x2, right at the deer, and we'll know that x2, we'll know the value of x2. All right, if we go over here, our x2 is now 37. But our vi is unknown. We do know that we have an acceleration, whoops, in the wrong place, acceleration going to the left with strength a0. And we know that that value is this. And of course, we still know that. All right, so it's much the same kind of thing. We still need to know where the car is when you start to brake, but we don't really know that. We're going to have it in terms of our unknown VI. But we can still say that x is VI delta t. So x1, oops, let's do it this way. Put delta x that way. So x1 turns out to be VI times the time. And then, so that's where we are. And then we don't care about the time in the second half, just like before. So we're going to use the same equation, and we're going to say that v final squared equals v initial squared plus 2a times x2 minus x1. We end at 0, that's easy enough, and we have vi squared plus 2 times the minus a0 that I have here times x2 minus v1 t1. So not particularly pretty, but probably solvable. 0 is vi square plus, let's even do minus 20 meters per second squared, that's this thing, times 37 minus vi times 0.5 seconds. And we look at that and we say that is, believe it or not, still just one equation and one unknown, so it should be entirely possible to generate a solution to it any way that you choose. You might use quadratic formula, you might complete the square if you're a little crazy, or you might do what I'm going to do, which is you're going to run it through a graphing program. So here I've gone to Desmos and I graph the function f of x equals x squared minus 20 times 37 minus x times 0.5, which you might recognize is the same as our vi square minus 20 37 meters minus vi times 0.5 seconds, and this is meter per second square. And we set ours as 0, so I asked Desmos, find me the 0 of that, and it did. Let's undo that. It did. And so we can see that our value of velocity would be this. So our best possible velocity before we hit is 22.658-ish meters per second. Wow, that's way too much sig figs. We have at most 2, so we should probably round to 2 places. So 23 meters per second, and that's what Mastering Physics wants. I'm going to say that actually in this case, Mastering Physics is a little wrong on that, because if we're going more than this value, we will hit the deer. So really, if I'm going to round to 2 sig figs and be safe, you probably should say 22, even though we're closer to 23. There's a statistical argument that we don't really know that, but this is a case where, as an engineering viewpoint, we should definitely say we should err on the side of caution. And so we get, but it should be 22 or 23. This is a complicated problem. If you found it multi-stage and weird, you're right, but it's the kind of thing you are asked to sort of at least be able to conceptualize out.